In example 1, for a function f, the derivative function yielded the following critical points. Critical points are points where the first derivative would be equal to 0. So that means at x equals -5, our first derivative has a value of 0. At x equals 3, it has a value of 0. And at x equals 6, we have a value of 0. Those are candidates for extrema, for local maximums or local minimums. Now what we need to do is look at what's happening on those intervals in between to determine what actually is happening. We're told in part A that f prime of -6 is equal to 3. That means that at -6, our first derivative function is positive. So on this entire interval, anywhere where x is less than 5, the first derivative will be positive. We're told that f prime of -4 is equal to 2. Is equal to positive 2. So again, our function is positive on that entire interval. Meaning we know that over this interval, our function is increasing the entire time, but the first derivative equals 0 at -5. In this case, though, we don't have a maximum or minimum. What we would have is a function that's increasing, levels out for an instant, meaning the instantaneous rate of change becomes 0 or the graph becomes horizontal for an instant, and then continues increasing. Since the sign of the first derivative didn't change from one side of that 0 to the next, we have neither a maximum nor a minimum. Which is again why we refer to these critical values as candidates for extrema. In this case, we had a point where the first derivative was equal to 0, but we don't have a maximum or a minimum occurring. Now we'll take a look at f prime of 2. Our derivative function is still positive, but then f prime of 4 will be -8. So our derivative function will be negative. In this case, we see that the sign of the derivative changes at x equals 3, and we have a function that was increasing, hits that 0 and changes to decreasing, which tells us that we have a local maximum at x equals 3. Then in part C, we're told that f prime of 5 is going to be -2. So the first derivative is still negative in that same interval. And then on the other side of x equals 6, we're told that f prime of 7 is equal to 3. So we get a positive value for the derivative. Meaning we have a function that's decreasing, and then at x equals 6 changes to increasing. And that picture, that quick sketch, shows us that we have a local minimum occurring at x equals 6. To summarize all that again, we started off with critical values, which is where our x coordinate is, where our x value makes the first derivative equal to 0. Then we have to investigate those intervals in between. If the sign changes, then we have a maximum or minimum, depending on the behavior of the function. If the sign doesn't change, then we have a case like what's happening around x equals 5, where our function just continues increasing through that interval. Since it doesn't change direction, we don't end up with a maximum or minimum.